So in this video, we are going to capitalize on the information that we've gained from our distribution process, and we're going to start considering free body diagrams of the substructures that make up this beam in order to determine the required bending moments and shear forces, because our moment distribution process has given us the bending moment at joint B, and it's given us the bending moment at joint C, but we still have a lot of other shear forces and bending moments to consider, not least of which are the span moments. Moving on, let's think about member AB first of all. So let's start off by sketching it out. Okay, so remember, this is a free body diagram, so we're not drawing on the actual supports themselves, but all we want to do is draw on the forces or the moments imposed by those supports. So we've got VA, representing the vertical reaction at pin support A, and VBL, which represents the vertical reaction to the left, or rather it represents the shear force to the left of joint B. So we have two unknowns in this particular free body diagram, and so we're going to use two of our equations of equilibrium to determine those unknowns. So I'm going to start off by considering the sum of the moments about point B, which is going to yield VA. So sum of the moments about point B must equal 0, and I am going to assume a sign convention where clockwise moments are positive. 3, so plus 3 times the vertical reaction at A, minus the moment, which is 21.87, because remember it's anti-clockwise, minus 10, the UDL, times it acts over 3 meters. It's triangular, so I'm going to multiply by a half, and the resultant of that load will act 1 meter out from what is essentially the base of the triangle, which would give me a lever arm of 1. And that all equals 0, and we'll notice the only unknown here is VA, so we can solve for VA. So VA is equal to 12.29 kilonewtons. So everything in this phase of the solution, in this free body diagram phase of the solution, is all going to be solved using equations of equilibrium. So now we can simply evaluate the sum of the forces in the vertical direction. So we have VA, which we just worked out, so that's 12.29 minus 10 times 3 times a half plus VBL equal to 0, and that will give me VBL equal to 2.71 kilonewtons. Okay, and because that's a positive number, that means that that force acts in the direction that I assumed, which was upwards. Let's just have a little think about what that means for the shear force diagram. We're jumping ahead a little bit. If I was to sketch out the member from A to B here, what would we say? Well, our shear force at A is going to be, or rather our reaction at A, which is also equal to our shear force at A, is going to be upwards of 12.29, so it's positive. On the right hand side, VBL is also going to be an upwards pointing shear force with a magnitude of 2.71. So if you like, that's your 12.29, there's your 2.71, and I have to get from this point here over to this point here in my shear force diagram. Now, because the magnitude of the distributed load is linearly varying, well, that means that the slope of the shear force diagram will be linearly varying, because you'll recall at some point in the past you've seen this relationship dV dx equal to minus Q, where Q here represents the intensity of loading, and what that's simply saying is that the slope of the shear force diagram is equal to the magnitude of the load intensity at a given point. Now, the magnitude of the loading at A is small compared to B, which means the slope of the shear force diagram will be small. So it starts off horizontal, and the slope increases as the magnitude of the loading increases up to 10. So we're getting a steeper and steeper curve as we get down to our 2.71. So that's what the shear force diagram is going to look like between A and B. Now we will notice as well that we have, at some point, our shear force becomes 0. We also know that where the shear force is 0, bending moment is a maximum. Moving on, let's think about member BC. Sketching it out again. Okay, so following the exact same procedure as before. Now just remember, we have cut the structure at B and we've also cut it at C. And in making those cuts, we revealed the bending moment from B to C, but we also revealed the bending moment back from C to B, which is this 150. So don't forget about that 150 as well. So taking the sum of the moments about point B, and solving for our only unknown, VCL, the shear force to the left of joint C, is equal to 34.83 kilonewtons, pointing upwards. Now taking the sum of the forces in the vertical direction, and so VBR is equal to 5.17 kilonewtons, again pointing upwards. So the last member to consider is member CD, and that's quite a straightforward one. Okay, so the only unknown for this free body diagram is VCR, and by inspection we can, by evaluating the sum of the forces in the vertical direction, we can say by inspection that VCR is 150. So VCR has got to be 150 kilonewtons pointing upwards to balance the externally applied load pointing downwards with the same magnitude. So at this point, it's worth just jumping back a second up to member BC just to do the same exercise in thinking about what the shear force diagram would look like for that member. So if I was to sketch member BC out, so we've got VBR is equal to 5.17 pointing up. So if this is B and this is C, we would have our 5.17. But VCL was equal to 34.83. So, and that was also pointing up. So that's 34.83. Now, like before, I've got to get from over here to over here in my shear force diagram. And again, because we have a linearly decreasing magnitude, we are going to have a curve. And that curve is going to be steepest where the load intensity is at its highest, and that is at joint B. So we're going to start off with a steep curve, shallowing out or becoming shallower and shallower as our load intensity reduces. So it's going to curve like so. And again, you notice that at some point here we have a zero shear, which will mean that there is going to be a local maximum, or indeed potentially a local minimum, but it's going to be, in this case, a local maximum in our bending moment diagram. So that's the only thing that we have left to consider now. What are those span moments for member AB and member BC? So to work out the span moment in member AB, what I'm going to do is make a cut in that member at some undefined distance x along the member, and I'm going to determine an expression or a function for the bending moment in that member as a function of x, because the bending moment diagram, remember, is simply a curve. It's a polynomial. And if I want to find the local maximum in a curve, what I can do is take the function that describes that curve and I can differentiate it, and that will give me an expression for the slope. And if I set that expression for slope equal to 0 and solve for x, what I'm essentially doing is I'm solving for the position or the distance x at which the slope is 0, and that will be the local maximum or minimum for that curve. So span moment AB. Okay, so I have taken a vertical cut through my structure at some distance x to the right of point A. Okay, now that would mean that the magnitude of the loading at the point I made that cut was simply going to be 10x over 3. Now, what I want to do is determine an expression for m as a function of x. How does that bending moment vary as x changes? Okay, so to do that, I'm going to take the sum of the moments about the cut, let that equal to 0, state my sign convention as usual. mx equal to 12.29x minus 10x cubed over 18. Okay, so that's describing the bending moment diagram essentially for that region of the structure. And this is where our basic calculus comes into play here. So we have a curve. it is a function of x, and we want to find out where is the local max or min in that curve. And we know that to do that, we would differentiate that curve with respect to x. So what I'm going to do is say d dx of m, a function of x. So taking the first differential with respect to x of that function is going to give me 12.29 minus 3 times, let me see, 10x squared over 18. So 3 times that, and that all equals 0. Okay, I want to solve for the point at which that expression equals 0, because that's where my local max or min occurs. Letting this expression equal 0 and solving for x equal to 2.716 meters. Okay, so 2.716 meters to the right of A is where my bending moment is a maximum. So what I'm going to do now is I'm going to take that value of x, I'm going to plug it back in here to determine what is the actual value of the bending moment at that location. When you work it out, it gives you 22.25 kilonewton meters. Now we can do the exact same exercise for member BC to work out the span moment in that member. Okay, so this time I have made my cut at some distance x to the left of C. So taking the sum of the moments about the cut once again. Okay, and we're going to do the same thing, differentiate that, let it equal to 0. And so x would equal 7.465 meters to the left of joint C. And plugging that value of x back in here, I can determine that m, the bending moment at that maximum, at x equal to 7.465, would equal to 23.34 kilonewton meters. Excellent. So at this point, we have determined all of the various different moments and shear forces we need to fully specify, fully define, fully draw the shear force diagram, the bending moment diagram, and the qualitative deflected shape. And so that's what we're going to move on to do in the next video.